In the previous lecture, I introduced the concept of momentum and indicated how this conservation principle can make it easier to handle certain mechanics problems. We are going to take one more step in the direction of using conservation principles and work with energy conservation in this lecture. You have been hearing about work and energy maybe since your 10th, 11th grade. I am going to show you in this lecture how these concepts arise naturally when I try to eliminate the time from the equation of motion. Recall that the equation of motion is F is equal to m dV over dt, but at times it may so happen that I am not interested in the evolution of the system as a function of time. For example, if a particle is falling in the gravitational field of the earth, I may be interested in knowing what is its velocity at a certain height from the earth, and I do not have to really worry about time. In such situations, we eliminate time. And how do we do that? If I write F equals m dV dt, this is equal to, I can write as m dV dx dt. I am taking only one dimension into account right now. For 3 dimensional cases, we will see later what happens. So, F, let us take now only x direction, is equal to m d Vx dt, which I wrote as m d Vx dx dt, which is m Vx dVx over dx, which is m over 2 d over dx Vx square. So, you see, I have now related the force directly to velocity, and there is no need to integrate over time. Let us see how it makes our problem solving slightly easier. Let me go back to the example of gravitational field, since I mentioned that earlier. Suppose I want to know the velocity of a particle in gravitational field. If the particle is moving in the radial direction, then I have dr dt is equal to the force which is in radial direction itself, which is minus g m over r square, or it should be d 2 r by dt square, because I am talking about the acceleration and the mass. And therefore, I have d 2 r over dt square as equal to minus g m over r square. This equation is very difficult to integrate with respect to time. On the other hand, let me apply the trick I used earlier in writing d 2 r dt square as d over dr dt times dr dt, and that gives me Vr d over dr Vr, and therefore, half d over dr Vr square is equal to minus g m over r square. This is an equation which can be easily integrated with respect to r to obtain velocity as a function of the radial distance from the center or the height from the center of the from the surface of the earth. So, the need to eliminate t gives me a slightly different equation. Let me look at it slightly more carefully. So, I had written earlier f x equals m d Vx over dt, and by transforming this into the form d over dx Vx dx over dt, I got that Fx is equal to 1/2 m d over dx Vx square. If I integrate this equation, what I get is half m Vx at some position x2 square minus 1/2 m V at some position Vx1 square is equal to integration f x dx from position x1 to x2. Let us now interpret this equation. I am going to call this f x dx the work done by the force. I am going to call this quantity 1/2 mv square the kinetic energy of the particle. So, what it tells me is that the change in kinetic energy is equal to the work done by a force. Not only have I defined the work and kinetic energy for you, I have also obtained a relationship between the two, in that the change in the kinetic energy of a particle is going to be equal to the work done by a force on it. Although I have taken a one dimensional example, I will now generalize to a three dimensional example. This is a statement in one dimension of the work energy theorem, which we use in solving mechanics problems again and again. Let us see now if I can generalize it to three dimensions. So, work done I had written as f x dx in one dimension. In three dimensions, the work done is going to be the force taken a dot product with dl integrated from point 1 to point 2. Let me explain this. Suppose a particle is moving from one position to some other position, from 1 to 2. I can break this path into small segments of dl each, and for each segment I calculate the work done, which is equal to the force in the direction of that segment times the length of that segment, and integrate. So, that gives me the work done by this force. Notice that I have to then know as to which path I am going over. So, this is the work done. Let us see if this can be related to the change in the energy or kinetic energy of the system. So, work which is equal to F dot dl can be written as m dv dt times dl, and when the particle is moving along a curve like this, dl is going to be v dt, and therefore, I have work is equal to integration m v dot dv, and this is nothing but integration m d v square over 2. When integrated over, it gives me work is equal to half m v final square minus 1/2 m v initial square, and work as defined is F dot dl, moving over a curve from over a curve C from point 1 to point 2 is equal to delta K E. So, we have in general that the work done by a force is equal to change in the kinetic energy, and I am going to call this the work energy theorem. I emphasize again, when I calculate the work done, it is the work done by the force. Let me now ask a question, since I talked about a particle moving along a curve from one point to some other point. Is the work independent of the path, or does it depend on which path am I taking? So, if I calculate f dot dl from point 1 to point 2, is it the same whether I take this path or some other path or third path, or is it different? In general, the answer is that it could be different. The most simple example for this is the frictional force. Let us again take a one dimensional example. Suppose I take a particle from point 1 to point 2, one directly and one take it to some other point and bring it back here. You can see that the work done by the frictional force in this case is going to be much larger than the work done by the frictional force in this case. So, in general, the work done by any force depends on the path taken. Let us take another example of this. Suppose there is a force field where the force applied is in circular direction. That is, if a particle is here, it will experience a force, now that you know planar polar coordinates, in phi direction. Let me then take a particle from point A to point B through two different paths. Path 1, let it be this one, A to B directly, and path 2, let it be like this, A to C and C to B like this, let this point be C. In the first case, when I calculate f A B, it is in the direction of phi something, but the displacement dl is in direction dl r. So, f dot dl is 0, and therefore, work done A to B is equal to 0. How about work when I go from A to C to B? This is going to be work from A to C plus work from C to B. Work from A to C is like work from A to B, therefore 0, but this is not, because here the displacement and the force both are in phi direction. In fact, if f depends only on the radial distance, then work A C B is going to be the force at radius r times pi over 2 r, which is non-zero. So, if the particle moves in this force field from A to B through this path, by work-energy theorem is going to have a kinetic energy at this point. On the other hand, if it moves along this point, there is going to be no change in the kinetic energy. So, this is another example of the force field where the work depends on the path taken. Let us see what happens if the work done is path independent. So, we have seen two examples of cases where the work depends on the path taken, but there are many forces in nature for which the work done is path independent. That is, no matter which path I take, whether I go from 1 to 2 along this path or this path or this path, the work done from 1 to 2 is going to be independent of path. An example of this is the gravitational field, the work done when two charges move due to their Coulomb interaction. In this case, if I go from 1 to 2 and come back via other path from 2 to 1, work done, since their magnitudes are equal, is going to be positive in one direction, negative in the other direction, and therefore, in a closed path, work done is 0. So, we have seen two cases. In one case, the work may depend on path, in the other case, work may not depend on path. For the cases where work is path dependent are known as non-conservative forces, whereas when work is path independent, these forces are known as conservative forces. So, we just saw that frictional force is non-conservative. The force field like this is non-conservative. Gravitational force is conservative. These are important concepts. There are certain things I can do for conservative forces which I can't do for non-conservative forces, and that is precisely why I define these two classes. You will see later in your course in electromagnetism that this kind of E field or force field arises when magnetic field changes with respect to time. Let us now see then, if the work done for conservative forces, so I am focusing on conservative force, if the work done is independent of path 1 to 2, which is equal to integration f dot dl from 1 to 2, then I can write this as the difference between a quantity at these 2 points. I will interpret this in a minute, but for the time being let me call it the potential energy. Recall from your course in thermodynamics or the first law of thermodynamics in your 12th grade that a similar quantity, the internal energy, is defined in first law because the difference of the heat and the work done by gas is independent of the path taken on PV diagram. Similarly here, if the quantity f dot dl is independent of the path taken, it can depend only on the endpoints, and therefore, I can write this as a difference f of this quantity. I am calling this potential energy. How is it related to the force? We just saw that I define it as f dl is equal to minus from R1 to R2 as minus u R2 plus u R1. Therefore, for a small difference delta u is going to be f dot dl with a minus sign. The way then I interpret this is that the change in potential energy is the work done if I move a particle by applying a force opposite to the force field in which it is moving. For example, if I were to move it in a gravitational field, I will keep it in balance by applying a force opposite to the gravitational field. that is what this negative sign integrates, and the work I do, not the force field, but the work I do in moving the particle is equal to the change in the potential energy. That is the interpretation of potential energy. So, potential energy is equal to the work done by the person who is moving it in moving a particle in a force field, and I am moving it slowly, so that there is no change in kinetic energy or anything, keeping it in balance all the time. So, let us see, if I apply the work energy theorem to this case, what happens? Or let me again write, I am talking about conservative forces, then F dot dl I have defined as minus u r2 plus u r1 when I am going from point 1 to point 2. This by work energy theorem is nothing but K E at point 2 minus K E at point 1, and this is going to be equal to minus u at point 2 plus u at point 1, and if I reshuffle, I immediately get that K E at 2 plus u at 2 is equal to K E at 1 plus u at 1. I call this quantity kinetic energy plus the potential energy as the total mechanical energy, and as a consequence of the work energy theorem and the conservative nature of the force, I get it that in conservative force field the sum of the kinetic and potential energy, and therefore, the total mechanical energy remains a constant. You see, at 1.1 is the same as at 0.2, and therefore, it is same as 0.3, 0.4 and so on. This is known as the law of conservation. Energy. So, let us see what we have seen so far. We have seen that I can define the kinetic energy as equal to 1/2 mv square, work as F dot dl integrated over, work may be path dependent, it may be path independent. This I call non-conservative force, and this is conservative force, and if it is conservative, I can define a quantity called potential energy. Actually, I should really say it is the difference in potential energy, which is defined as u r2 plus u r1 is equal to F dot dl between 1 and 2, and we saw that change in the potential energy at a position is equal to minus F at that point times dotted with dl. And for conservative forces, K E plus u is a constant. The two key concepts that we have come up in this discussion is work energy theorem and conservation of total mechanical energy. Before their application and discussing more about them, I want to spend some time to get a feel for the potential energy. I define the potential energy as U R2 minus U R2 plus U R1 as integral F dot dl from R1 to R2, and I am not writing any path in this because this is defined only for those forces for which the work done is path independent. If you write it like this, you see that the change over a small distance is equal to minus F dot dl, and that gives you the interpretation of potential energy as the work done by you, by the external agency, to move a particle slowly in the external field. Also, notice that it is the difference in the potential energy that has meaning. The usual practice is that you take a reference point R1 and put the potential energy to be 0 there and define the potential energy at all other points with respect to that point. Let us then take two examples for this. One, the spring. System in which if a particle is displaced by distance x from the equilibrium position, the force F applied by the spring is minus kx, and therefore, if I were to calculate u x2 u x1 minus u x2 plus u x1, this would be equal to F dx from x1 to x2, or according to our interpretation, the difference in the potential energy from point 1 to point 2 is going to be the force is applied by me. So, minus sign F dx from x1 to x2, which then becomes u x2 minus u x1 is equal to integral k x dx from x1 to x2, which is equal to half k x2 square minus half k x1 square, the formula you are well familiar with. Also, I take in this case u at x equal to 0 to be 0, and that is my reference point, and therefore, I write in general u x is equal to 1 half k x square. Also from this, the force is given as du dx by definition, and this you see comes out to be minus kx. Let me elaborate a bit on that, because I did it in 3 dimensions. We had F dot dl is equal to minus u r2 plus u r1, and therefore, for a short distance I had F dot dl with a minus sign is equal to delta u, and in 1D that will give me F equals minus du dx. Let us take another example, that of gravitational field, in which the force F as a function of r is given as minus g m m over r square. So, if I were to calculate the potential energy at a point r2 with respect to r1, this is going to be minus F r, and I move the particle along the radial line from r1 to r2, and this gives me integral g m m over r square dr from r1 to R 2, which is equal to minus G m m over R 1 R 2, and therefore, I get U R 2 minus U R 1 as equal to minus G m m over R 2 plus G m m over R 1. In the case of gravitational field, I take U reference point at infinity. So, U R 1 at infinity to be 0, and that defines my U uniquely as minus G m m over R. You can again see that the force in the radial direction is going to be minus du over dr, which is minus G m m over R square. So far, you notice I have been focusing on one dimensional cases, and that is because the work done or the energy, whether kinetic or potential, are all scalar quantities, whereas the force and the displacement are vector quantities, and the two are related by this dot product, which becomes quite easy to work with in one dimensional case. For three dimensional cases, I will talk about later. We have special techniques to check things out. So, from now on, I am going to concentrate on 1D case and talk about energy conservation in one dimension. As I had mentioned in the beginning of the lecture, that a motivation to develop the conservation principles of linear momentum and energy is to make solutions of problem easier. Let me now, after having developed these concepts, take 2 or 3 examples where I show how these principles are applied in solving mechanics problems without really going into integration of the equation. As the first example, let us take the case of a bead sliding over a vertical ring of radius r, and I want to know what will be its velocity when it has fallen by a distance x or moved by an angle theta from its initial position. If I were to integrate the equation of motion, I would have to take care of the force that is applied by the ring, the gravitational force on the bead, and so on. If I want to apply the energy conservation principle, since I know that in this case the gravitational field is conservative, so the net energy should remain a constant. So, K E plus U at the top, that is this position, should remain the same as K E plus U at say theta. K E at top is 0. Let me take the U to be 0 here at the ground, so that at the top it is going to be m g times 2 r if the height, if the mass of the bead is m, and this should be equal to K E at theta or this distance x plus U at this point is going to be m g 2 r minus x, and that gives me K E at this point 1/2 m v square is equal to m g x, or v equals square root of 2 g x, a well known result. I use this simple problem now to a slightly more complicated problem, where I would ask the question, if there was a particle It is a very standard problem and probably I have solved it in the past in one of the previous lectures. Now, want to solve it slightly differently here. If there is a particle which is sliding on top of a sphere, I want to know at which point or at what distance from the top x does it fly off the sphere. So, in this case I know at this point it requires a centripetal force to go over this circular radius, circular path. So, at this point the forces on this are mg in this direction and the normal reaction in this direction. The component of mg towards the center gives it the centripetal force, and therefore, if this angle is theta, so is this, you have mg cosine of theta minus n is equal to m v square over r. As long as n is non-zero and pointing outwards, I know the particle is on the sphere. N equals 0 implies particle loses contact with the sphere. So, that at that point I am going to have m g cosine of theta is equal to m v square over r, and therefore, r cosine of theta is equal to v square over r, v square over g. I have already calculated v square. So, we have r cosine of theta equals v square over g, and if I look at this problem again, I have this r, this is theta. So, that this is r cosine theta, and you see that r cosine of theta is equal to r minus x, and we have already calculated that v square is equal to 2 g x, and therefore, I have r minus x equals 2 x or x equals r over 3. So, when it travels down a distance of r by 3, it is going to fly off the sphere. Another problem where I am going to now combine the principle of momentum conservation and principle of energy conservation is going to be solved now. Let us take a particle of mass say 0.1 kilogram traveling in this direction with a speed of 1 meters per second. It hits another particle of say 0.5 kilogram, and after the collision the two particles travel, one with speed v 1, this is 0.1 kg, and the other particle with a speed v 2, this is 0.5 kg. We wish to find v 1 and v 2. Although you may have seen this problem in the past, it does not hurt to solve a simple problem to start with. So, first I apply linear momentum conservation. Because there is no external force, these things are moving in a horizontal plane. Therefore, I must have 0.1 times 1, that is the initial momentum, must be equal to 0.1 v 1 plus 0.5 v 2. This is the momentum to start with. This particle has no velocity, so 0 momentum, and therefore, I have 1 equals v 1 plus 5 v 2. That is my equation 1. Since there is no external force, so potential energy remains the same. The kinetic energy should remain the same if we assume the collision to be elastic, and therefore, Ke initial is equal to Ke final. I have not taken potential energy u into account because it remains the same, or on a horizontal surface it does not change, and therefore, I must have 1/2 times 0.1 times 1 square, that is initial kinetic energy. Final kinetic energy, both particles are moving, and therefore 1/2 times 0.1 V1 square plus 1/2 times 0.5 V2 square, and this gives me half cancels. This gives me 1 equals V1 square plus 5 V2 square. This is my equation number 2. Equation number 1, let me rewrite it once more. 5 V2 is equal to 1. Solve these two equations to get V1 and V2. Let us substitute. So, I take the value of V2, which is 1 minus V1 over 5 from the first equation, and substitute in the second equation to get 1 equals V1 square plus 5 over 25, 1 plus V1 square minus 2 V1, this is 5, and therefore, I get 5 is equal to 5 V1 square plus 1 plus V1 square minus 2 V1, or 6 V1 square minus 2 V1 minus 4 is equal to 0, or 3 V1 square minus V1 minus 2 is equal to 0. This gives V1 equals 1 plus minus square root 1 plus 4 times this 24 over 6, and that gives you either 1 meters per second or minus, this is 5 2/3 meters per second. This is a trivial solution, as if the collision did not take place, and this is the solution of interest, in which the particle 1 hits particle 2 and goes back with this much velocity. So, I get V1 is equal to minus 2/3 meters per second, and if you recall, I had 1 equals V1 plus 5 V2, and this gives me 5 V2 is equal to 5/3, or V2 equals 1/3 of meters per second. I gave these two simple examples in one dimensional case to show you how the conservation principles make solution easier. Notice that I did not have to integrate over a force over time. All I did was use the fact that momentum is conserved and energy is conserved. After giving these simple examples, I want to go back to the potential energy and get little more feel for it. Although I am going to restrict myself in one dimension, it teaches me a lot. Suppose there is a potential energy curve like this. So, this is u x versus x. I can simulate this by taking a wire in this shape and let a bead move over it, because the height would be proportional to the potential energy because of the gravitational force. There are different points I want to identify in this. This is the maximum of potential energy, where I have du dx is equal to 0 and d2u over dx square less than 0. There is this point where I have du dx is equal to 0, and this is a minimum, and therefore, d2u dx square is greater than 0. At this place, du dx is less than 0. On this place, du dx is greater than 0. So, let us look at these 4 points and see what I can say about them. Let us start with the maximum of the potential energy, where I had du dx equals 0 and d2u over dx square is less than 0. So, you notice since it is 0 here, du dx on this side, du dx is 0, and as x goes up, since d2 dx square is less than 0, du dx on this side must be greater than 0, as is also evident from the graph. Similarly, on this side du dx is less than 0. So, if I were to look at the force F x, which is equal to minus du dx, you can see that on both the sides the force would be pointing away from the maximum. So, looking at the maximum, I see that the force points away from the maximum of potential energy. So, any particle at the maximum of the potential energy is going to be running away from it. Let us look at the minimum or a minimum. At a minimum, du dx is again 0 and d2u dx square is greater than 0, and therefore, from as you go towards the positive x side, slope is positive, on this side slope is negative, and therefore, f x, which is minus du dx, is going to give you a force on this side, which is going to be towards this, is going to be less than 0 for x greater than x min, and is going to be less than greater than 0 for x less than x min. So, you see the force points in the positive direction if you go to the left of minimum, and in negative direction if you go to the right of the minimum. Therefore, the force always points towards minimum. So, let us write the force points towards the minimum of the potential energy. So, any particle at the minimum would tend to move towards the minimum if displaced from there. So, let us see now, if I had a curve like I plotted earlier, what would happen? If I had a particle here, it will just come down this way or this way. If I had a particle here, if I displace, it will come down back to the minimum. At these points, the force is in this direction, at this point the force is in this direction, at this point the force is in this direction. This is F, F, F. F is always opposite to the slope. One interesting thing that comes about then is, if you are at a minimum and particle is displaced from it, it tends to come back. In fact, if the displacement is very small, you will see that it will start performing simple harmonic motion. Let me explain that. So, near a minimum, and let us call that minimum x equals x 0, let us take this one. I have u x slightly away from the minimum as, by Taylor series expansion, u x 0 plus du dx at x 0 x minus x 0 plus 1/2 d2u dx square at x 0 x minus x 0 square. Since this is a minimum, du dx at this point vanishes, and therefore, I have u x as equal to u x 0 plus 1/2 d2u dx square at x 0 x minus x 0 square, and therefore, the difference in the potential energy u x minus u x 0 is equal to 1 half. This being a minimum is a positive quantity. So, let me write this as k x minus x 0 square for small displacements. If I call this u y by taking u at x 0 to be 0, because as I said earlier, you always define potential energy with respect to a particular point, is equal to 1 half k y square, where y I take to be x minus x 0, or the displacement from the minimum. You can see that the potential energy changes like a spring, and therefore, any particle displaced from here would execute simple harmonic motion with the characteristic frequency of k over m, where k is given by d2u dx, or the second derivative of the potential energy, and this is going to be square root of 1 over m d2u dx square at x 0. So, what we have done in this lecture is try to eliminate the time from the equation of motion, and consequently we found that we can relate certain quantities which depend on the position. These quantities are energy, kinetic energy, or the potential energy, to evaluate the velocities at different positions. We also discussed in short, very briefly, what the conservative and non-conservative forces are. We have restricted ourselves to one dimensional motion in this case, and the next lecture I am going to generalize to 3-dimensional motion and see how really we can answer the question whether a force field is going to be conservative or non-conservative.